So let A be a subset of real numbers such that it is non-empty and bounded below. So we are going to prove that supremum of the minus of this set is equal to minus of the infimum of A. So let me say let S be the infimum of A. Then by definition, for every A in A is bigger than this infimum, right? So A bigger or equal. And for every epsilon, positive epsilon, there exists A0, let me say, in the set such that if you sum infimum with this epsilon, you will get bigger number than A0. So let me label them as the following. This is I. This is I. Okay. So if you multiply each side, each inequality in the both cases by -1, you will get the definition of a supremum of minus A as following. So let me just multiply them without changing anything. So for every minus A ya da şöyle öyle diyeyim. A minus A is less or equal than minus S. Tamam. I for every epsilon bigger than 0, there exists A0 in A, or let me put minus A0 in A, minus A. Okay, minus A0 in minus A, such that minus A0 is bigger than minus S plus, no, minus epsilon. Okay, now it's nice. So remember the definition of supremum. So the supremum of some set, in this case it is minus A, is bigger than every number in the set. Okay, first condition is checked. And for any given positive number, there exists a number in our set such that this number is bigger than supremum minus some epsilon in the given, in the very beginning. Okay, so this is the definition of supremum of minus A. So S is satisfying the definition of supremum minus S, of course, because at each case it is minus S. Okay, supremum of minus A. Now let's say supremum A is S. Okay, denote S. Sure, let me define it like this. Supremum A. Okay, then what is the definition of supremum? First, it is bigger than every number in the set. For any A in A, S is bigger or equal than A. Now in the second condition, for any given positive real number, there exists A0 in the set such that supremum minus epsilon is less than A0. Okay, again we are going to multiply it by minus, right, because we want to talk about this infimum of some minus set. Okay, so by the way, this minus A is defined by the following: minus A for any A in A. You just multiply by -1 in each for each element in the set. So let me again rewrite this inequalities for any A or minus A in the set minus A. So minus A is less or equal than minus S. No, not this, like this. The other way around. Other way around. In the second condition, for any epsilon bigger than 0, there exists a minus a0 in the set minus a. By the way, I'm using the existence of a0 from the first condition. Okay, barely the definition of supremum of a, nothing more. Then minus s plus epsilon is bigger than minus a0. Okay, so this is let's look at it. This minus s, okay, in this case behaving like the infimum of this minus a. Okay, so yes, everything is okay. So by definition of the infimum, this minus s is then infimum of a, because it satisfies every condition that the infimum should satisfy. And since we know that infimum and supremums are unique, as in the first case, so we are finishing like that. Let us a and b are non-negative subset of real numbers which are bounded above. I mean, a and b has some bounds, for example 5, 10, 1,000, million, but they are bounded. So the claim is, if you multiply them, and multiplication defined as follows. Okay, a multiply b as a b, you just multiply each element. Okay, so define, let us use this supremum a and supremum b's definitions. So for any a in a b, sup is bigger or equal than a, sup b is bigger or equal than b. So if you multiply these both inequalities, since they are positive, a and b are also positive, right? So we have supremum a, supremum b bigger or equal than ab. For any a in a, b in b. So it means that it is an upper bound. So sup a multiply sup a is an upper bound. AB. Now we show that this is indeed least upper bound. So using the definition of sub b sub a, and given any epsilon bigger than 0, so we have a0 in a, b0 in b, such that this sup a minus a minus epsilon is less than a0, supremum of b minus epsilon less than b0. So we can multiply each side. This is also positive, this is also positive, so multiply them. So we have supremum a, supremum b minus epsilon, supremum a plus supremum b minus epsilon is bigger than or less than, okay, this part is less than a0, b0. But this is the second condition of the definition of being a supremum, right? Because given any epsilon, of course it can be very small, as long as this epsilon does not exceed the sum of these supremums. So we don't care about bigger epsilons, right? You can always arrange these epsilons because the first one is fixed, but for any given other epsilon or some multiple of epsilon, these inequalities would be satisfied. So you can have a lot of control on these epsilons or multiples of them. So you can make this term as small as possible. By the way, it is very obvious from this inequality, so that this satisfies the definition of supremum. So sub A sub B is actually supremum of AB. Okay, now we can assume one of the supremum is bigger than other. Okay, let's assume supremum A is bigger or equal to supremum B. Okay, now given any C in the union, so if it is from the B, this C is from the B, then this C is less than supremum B, and since supremum B is less than supremum A, so this C is less than supremum A. So C is less than supremum A by the definition. So we have an upper bound. So let's check the second condition. Given any epsilon, so we are going to use the bigger one, supremum A's definition, second condition. So there exists some A0 in the A such that supremum A minus epsilon is less than A0. Okay, but this A0 is also in the union, so our definition holds. A0 is in A, so subset of A union B. So this is finished. It satisfies the old definition of supremum of this union, and since supremums are unique, we are finished. Using the same idea, we can also conclude the following second condition: infimum of the union is also preserved by the minimality, mean inf A inf B. By the way, we are using this boundedness to talk about the existence of this kind of supremums. Otherwise, we cannot talk about these supremums. That's why we are needing this kind of conditions. Of course, also non-emptiness is also a thing. So that's the proof. Now let us assume that our set is consisting of this kind of numbers: 2, 0, 0, 2, 0.22, and so on. So we can formalize the formula for this set generator. Okay, this is like a sum from the number k equals to 1, let me say. Okay, and this is natural number. Okay, so in this case, in this formula, we can understand that this kind of numbers are just partial sums of this general formula. Okay, we claim that the supremum of this set is 2/9. How can we prove it? So as you can observe that each number is increasing, right? With of course, since everything is positive and you are adding some other numbers, so it is increasing. Is it bounded? Yes, it is bounded, because as you can see, this is a fraction decomposition, right? So in this notation, so they, for example, never exceed the number 1, right? Because they always start with 0 point something. So it is bounded and increasing sequence. So by monotone convergence theorem, if you remember from the earlier courses, this has a limit as the supremum of the set. So if we can evaluate the limit of this set, in this formula, we will end up with the supremum of the set itself. So let me just calculate the limit. So limit of this general formula k equals to 1. So it is by definition the infinite series, right? From 1 to infinity to the 10 to power minus k. So, but we know how to calculate this, but okay, let me just recall you. When k is 0, starting from 0, and if you have a number a to the power k, so definition says that 1 over 1 minus a is the summation, right? If and only if this a is less than 1. Otherwise, this series does not converge. So, what is our general formula? We can mimic this formula as this is also equal to 2 over 10 multiplied by this infinite series in the green form, 10 to the power minus k. As you can see, our number is 1 over 10 now, right? Our a is 1 over 10. So by this formula, we have 2 over 10 and 1 minus 1 over 10. So this part is 2 over 10, 10 over 9. They cancel. As you can see, we have proven our claim. So as a second step, let me claim the infimum. Infimum of a is 0.2, right? Because it is the least number that it can that we can have, right? This is the starting point of this sequence. Okay, if we can consider it as sequence, but it is very easy to understand because it is increasing. So the least number is the starting point, which is 0.2. But you can prove by using epsilon definition of the infimum. Exercise, prove using epsilon definition. So now let us look at this set B. So this is also a decimal fraction of numbers, but as you can see, it starts with 0. 0 point some decimal fraction. But these numbers are only coming from 0 or 1. So this is, for example, let me make an example. For example, 0.111001 is in the set, right? Because it is starting from 0 point and every number is either 0 or 1. So we are asked to find the supremum of the set B. So what is that? So we have very good prediction on the supremum of B, right? Because as you remember, supremum is the least upper bound, but it is an upper bound. So how can you make an upper bound still from this set? Okay, so if you put 1, because you don't have much of a choice, 0 or 1. So if you choose 1 for each decimal, you get the upper bound, right? Because whenever you have in the set, it will not probably everything is 1. If it is 1, then it is our element too. But there is something wrong about our candidate, right? So what is our candidate? Claim sup B is 0.11111 as goes to infinity, right? But there is no such element in our set. But it does not have to be in our set, right? For example, consider the open 0-1 interval in real numbers. So supremum of this set is 1, even though 1 is not in the set. Of course, it is very natural, by the way. So, but this is our claim, right? So this is obviously upper bound. Okay. By the way, we can compute this number. So it is like an infinite set from k equals to 1 over 10 to k. to infinity. So it is, by the definition, 1 over 10, 1 over 1 minus 1 over 10. It is 1 over 10, 10 over 9. So it is 1 over 9. So my claim is that the supremum of the set is 1 over 9. So so this proves the upper bound, right? Okay. 1 over 9 is upper bound. Right? Given any number in this decimal fraction, if it ends somewhere, even though every number is 1, it cannot exceed this 1 over 9, because 1 over 9 is equivalent to this decimal fraction. Okay, so this is indeed an upper bound. How can we show that it is indeed the supremum of the set? So as follows: given epsilon, okay, we need to find some B0 or A0 or whatever it is in the set, such that when you subtract epsilon from 1 over 9, you will find an element here that is bigger than this subtraction. Anyway, so we have two cases. If 1 over 9 minus epsilon is negative, then any number satisfy this. For example, e.g. 0.1 is bigger than 1 over 9 minus epsilon. This is in the element of set. This is the set. This is in the set. So this is satisfied. If not, then consider the sequence in the set. Consider the sequence, the partial sums. Okay, from 1 over 10 to the k. This is a partial sum sequence, right? Which is inside of the set, because each element of here is from the set, but not each element in the original set is in this form. Okay, because it can be 0 1 0 1 0, so it is not the formula of this. So we are going to use the limit of this sequence. We have calculated that the limit of this sequence Sn is 1 over 9, right? So we have shown that this is converging to 1 over 9 as n goes to infinity. So by the definition of limit, there are infinitely many numbers, infinitely many elements from the sequence in this in some interval that we are going to use. Okay, by the definition limit, we have a number. We have a number B0 from set in this interval. How can I show? 1 over 9 minus epsilon, 1 over 9 plus epsilon, right? But we don't, since our sequence is increasing, we don't have any number here, right? Because of this is the last point. Of course, this is not last. This is the limit. But we don't have any number in this second part. So, but we have a number in this set, in this part. I mean, what in this part? What is in this part? Let me just draw. This is 1 over 9. This is 1 over 9 minus epsilon. So we have a number here, since the sequence is increasing, and we have a limit, which is 1 over 9. That's why this provides me the existence of this number B0. So this proves my second case of my definition of being a supremum. That's why the proof is finished. Okay. So okay, let me maybe finish like this. 1 over 9 minus epsilon is less than B0 for some B0 in the set. Okay, that finishes my proof. Using the same idea in the supremum, you can also show the following. Infimum b is 0 using the sequence 0.1, 0.01, 0.001, etc. I'm using a sequence because I'm gonna use the same idea. Okay, I'm going to show that. Of course, I'm not going to show that, but I'm just hinting you to do. So this kind of sequence is gonna be 0, right? Because the number is decreasing, it is bounded, so it has a limit which is 0. So you are going to use the same idea to show that indeed the infimum of the set B is 0.